This is the second part of the lecture Pulse Oximeter and Pulse Co-Oximeter. We have in the first part I talk about a general background. In this part we'll talk about the first and second generation. Prior to move to the second part, I will make a small recap of the first part. We have a small introduction about the laboratory co-oximeter, which is a laboratory device used to measure the saturation of oxygen in the blood in the two forms, in the plasma as well as in the RBC. It's an invasive. It's invasive, so we take a blood sample from the patient, we hemolyze it, and we measure the different forms of the hemoglobin in this sample, which has four forms, which is the oxyhemoglobin, deoxyhemoglobin, metahemoglobin, and carboxyhemoglobin. Then we talk about, have a small introduction about the pulse oximeter, which is the topic of this lecture, as a replacement, a non-invasive replacement to monitor continuously the oxygen saturation in the blood. When we talk about the oxygen saturation, we talk mainly about the oxygen saturation in the RBC. We are not talk about the partial pressure of oxygen in the plasma. We only talk about the oxygen in RBC and not in the plasma. Then we have a talk about the respiratory gases available in the atmosphere, and we are interested mainly in the oxygen and CO2, and how this gas, the respiratory gas or the air, change as it pass through our airways. So it will firstly become humidified, so we will have more water vapor in this gas or in this air. Then we have talked about this gas exchanged in the lungs at the alveoli, where we have the supply of oxygen to the blood, and the removal of CO2 from the blood in this alveolar sacs. We said this is very important to our body because it helps to control the pH of our body, so the removal of CO2. Because as we said, the availability of CO2 with the water content in our blood will lead to have an acidic solution, which means that this will alter our pH. So by having continuously providing our blood with oxygen and the removal of CO2 from the blood will control the pH of this blood. Then we have talked about the carrying of the oxygen through the cardiopulmonary, the cardiovascular system to the rest of tissues, and we have talked about the tissue perfusion, which happened at the capillary level. In the capillary is a small blood vessel. It's around 1 millimeter in the length. It has a thickness of the wall thickness around 1 micrometer. The diameter of the capillary it's around 8 to 9 micrometers, which allow the movement or the pass of the RBC one by one in order to give their oxygen supply to the plasma, and secondly from the plasma to the tissue. As we said, the perfusion in the capillary is separated into two parts, in the first half and the second half. The first half we will have the movement of oxygen and the nutrients from the blood capillary to the tissues, and in the second half we have the removal of CO2 and metabolic waste, of course, as well as water. This due the difference in pressure inside the capillary and in the tissue. Usually the tissue pressure or the interstitial fluid pressure in the tissue is around 22 millimercury, whereas the pressure will start high at the arterial end of the capillary around 32 and will be dropped as it passes through the capillary, and this will be result in what's called the perfusion. So the tissue perfusion is essential to have a healthy tissue supplied with the nutrients and oxygen, and for the removal of metabolic waste and CO2. Then we talk about the respiratory gas measurement. We talk about the arterial blood, the arterial part exactly, the gases measurement in the artery. We have talked about two laboratory devices, which is the lab oximeter and the blood gas, which are both used in the reading of the pH, the partial pressure of oxygen in the plasma and the partial pressure of CO2 plasma, as well as the oxygen saturation in the RBC itself, in the RBC cells, sorry. So now we will start to talk about the second part of this lecture, which is the first and second generation. This part we will talk about pulse oximetry principle in general. Then we move to talk about the first generation principle. We have two methods in the first generation. The first method used to calculate the percent of oxygen saturation in the RBC is Beers-Lambert law, where we have two equations, two unknowns, and we can calculate this percentage by this way. Another method has been used to increase the accuracy and replace the previous method, which is the Beers-Lambert law, is the use of what's known as the R curve, and we will talk about this during the lecture, during this session. Then we will talk about the first generation source of the errors. We will see we have many types of the errors which was happening in the first generation, and this lead to error in the readings and measurement. Most of these errors has been fixed using the second generation, and mostly we are talking about the motion and perfusion. Finally, we will have a summary about what we have covered in this part. So we'll now start with the first part, the general pulse oximeter oximetry principle. So in the pulse oximeter, we use two wavelengths. First, this machine is used in the early 98s. It's a non-invasive measurement of the oxygen saturation, where we have a continuous measurement by comparison to the discrete invasive measurement using the either lab co-oximeter or the blood gas analyzer. It's safe. It's also inexpensive, where we have only the consumer will be the probe. We have also two types, as we said before. We have a reusable and disposable one. What we measure using this pulse oximeter is what we know, what's called the SpO2. It's the percentage of oxygenated oxyhemoglobin divided by the ratio of total hemoglobin and multiplied by 100%. We can see here the sensors, which we have talked previously in the part 1. We have, as we said, we have light emitting diodes, one red and one infrared. The red will have a wavelength which is 660 nanometers. The infrared will have a wavelength of 940. And the opposite side, we have the detector. It's a photo detector. This type of configuration, as we said before, is called the transmitted type, where the sensors, where the diodes, the LEDs in the one side and the detector is on another side. It can be used here. We can, as we also see in the first part, we can use this sensor or the pulse oximeter sensor in the finger or in the earlobe or different sides like the forehead. But this type is used in the finger. We will have a model for this type, which is the transmitted type used in the finger. The name pulse oximeter is due to the in the measurement by using the red and the infrared. We have AC signal and DC signals. We have the only AC signal available is the one related to the arterial pulse. For this, we have the name pulse oximeter. As we can see, as we see before, this diagram shows the pulsation of the pressure, blood pressure in the arterial side in the systematic circulation, whereas in the start from the venous, from the capillaries and the venous side, all the rest of the blood pressure is only a mean pressure, which means a hydrostatic without pulsation. Means like could be it's a DC signal. By comparison, in the arterial we have an AC and DC signal. What we measure real in the pulse oximeter, or what we interested in the pulse oximeter, is a measurement of this pulse pressure, especially we are talking about the arteries. So this is a model for the different absorptions happened for the red and infrared in the finger. As we said, we have AC signals and DC signal. The only AC signal in this model, this is a model, is for the arterial blood, this pulse in the arterial. We have also a DC signal, which is a absorption due to also the arterial blood. We have the DC portion, which related to the absorption by the venous blood, and finally we have the absorption due to the rest of tissues, which is the muscles, the nails, the bone and others. So as we see in the middle, in this model, we have different signals. We have an AC signal represents the arterial pulsation or pulsatile flow, and we have three DC signals, absorption signals, one to the arterial, one to the venous, and one to the rest, the other one for the rest of tissues. As we can see, we have an AC and DC signals. The only AC signal is, as we said, to the artery. It has the nature of being periodic with a specific waveform, and the rest as DC. Another point we notice in this diagram, the amplitude of the AC signal is relatively small by comparison to the DC signal. Also, another point we have this applied for the red and infrared signal. So as we said before, we are only interested in the pulsation and the AC signal of the arteries, which is small by comparison to the rest of the DC part, as we see here, DC. This is an example of a block diagram of a conventional pulse oximeter. This the finger, this is the probe or the SpO2 sensor. As we said, it's this type is a transmitted part. We put the finger between the LEDs and the photodiode. We have two wavelengths, the one 660 nanometer for the red and 940 nanometer for the near infrared. We have the photodiode, we have the LED drive, which make a switching between on-off between the red and infrared. We have only one photo detector, which is of one photodiode. This means we can make only either the red or infrared on at the same time. So once the LED, the red one is on, the infrared will be off. When the infrared is off, is on, the red will be off. And so for this, we have what we call the LED driver. The LED driver, which is switching the on-off between the red and infrared. And this is measured by the photodiode. The photodiode then signal is measured through an amplifier. This is a special type of amplifier. As we know, the photodiode will give us a current. So this amplifier is a current to voltage converter. It's a special type of amplifier. Then we have data acquisition and so on. This is a general block diagram for the pulse oximeter. As we said in the previous slide, which we talk about the model of the absorption of the different tissues made by the different tissues. We have an AC and DC signals. So the pulse oximeter we need to understand that we need different background. We need to understand electronics, as we see in this slide. So we have LEDs, we have photodiodes, we have current to voltage amplifier, we have a LED driver, and so on. We also have another important part, which is the signal processing, which is very important here in the design and of this pulse oximeter. As we see, we have an AC signal of a periodic nature, and also with a specific waveform we have a DC signals which is larger by comparison to the AC signal. We need to extract this AC signal to measure the oxygen saturation in the blood. Also, as we said, we have red and infrared. Each of the red and infrared will have absorption, as we said, by the tissues. Where the result, we will have an AC DC signal for the red and AC DC signal for the infrared. So another important part which will be covered in this part of the lecture is the signal processing. We said we have electronics and we have signal processing to understand really the design of the pulse oximeter and how we can improve this design or made better design for this. So why we use red and infrared? As we can see, this is the absorption of oxygenated oxyhemoglobin and deoxyhemoglobin made at a different wavelengths. As we can see at the 660, which is red, the absorption of the oxygenated hemoglobin is lower than the absorption of made by the deoxygenated hemoglobin, which is represented by this red curve. So the red curve representing the deoxyhemoglobin, whereas the black curve in this diagram represents the absorption by the oxygenated hemoglobin. So the red light is more absorbed by the deoxygenated hemoglobin, whereas the near infrared, which is 940 as we said, or we call near infrared, is mainly absorbed the near infrared by the oxygenated hemoglobin, and much lower is absorbed by the oxygenated ion. So at both wavelengths we have an absorption made by oxygenated hemoglobin and deoxygenated hemoglobin. The difference is that at the infrared, the oxyhemoglobin or the oxygen in the hemoglobin, the oxygen molecule will absorb more infrared. So to distinguish between red and infrared, we can simply say that the oxygen is more absorbed by will more absorb the infrared, whereas the deoxygenated will more absorb the red. This slide, we can see in this slide, we can see that the deoxygenated hemoglobin and the absorption of both red and infrared, and we see here in the oxyhemoglobin the absorption of red and infrared. As we said in the previous slide, oxygen will absorb more infrared by comparison. The oxyhemoglobin will absorb more infrared light than by comparison to the oxyhemoglobin, which absorbs more red light. So as we said before, we will now start to talk about the first generation principle. We have two principles or two methods for the measurement of or calculation of SpO2. The first method is used the Beer-Lambert laws. So as we see the Beer-Lambert law base, we have a light source and we have detector, and between we have the absorbing medium. We have this formula which summarizes the transmission through this absorbing medium. As we said, we have wavelengths. We have the red and infrared. Both of the red and infrared, from the signal processing point of view, will have two signals. The red will have an AC signal and DC signal after being absorbed by the tissues, and similarly the red. So the red and infrared both having a absorption, both have AC and DC signal. The nature of the AC signal, as we said before, it's a periodic with a specific form, similar to the one to the arterial pulse pressure. So it's similar to this one. Beer-Lambert law. If we make the use of two wavelengths, red and infrared, will have two wavelengths as we see here, and this will result in two unknowns, and we have two unknowns and we have two equations. The two unknowns is the oxyhemoglobin and the concentration of the oxyhemoglobin and the concentration of the deoxyhemoglobin. So we have two equations with two unknowns. We will then calculate the oxygenated hemoglobin concentration and oxyhemoglobin concentration and the oxyhemoglobin concentration. Finally, we will substitute them in this formula, okay, and we multiply by 100% by 100, and we get the percentage of the SpO2. So we have two concentration which are calculated from this two equations. Two unknowns are calculated from this two equation and substituted in this formula, multiplied by 100, and then we got the percentage of the pulse oximeter. Another method which is more accurate, which is replace the previous method, is the use of R curve. The R curve is more accurate. This R curve is obtained through the taking of blood samples from persons, subjects, we call them subjects. An experiment, each manufacturer will have subject, will take blood samples, and we will measure the ratio of the red and infrared signals, and we'll measure the real oxygen saturation using either a blood gas analyzer or a lab co-oximeter, and we create this curve. So this curve is created by having a subject. We take the samples. We measure first the blood, the ratio of the red and infrared using the pulse oximeter. Then we take this sample from this patient, from this subject, and we measure it by as we said before, a blood gas analyzer, either a blood gas analyzer or a lab co-oximeter, and we create this curve. However, this curve has a limitation because we cannot reduce the oxygen saturation of the subject below 85%. So what really happen? We reduce the oxygen saturation to a level higher a little bit than 85%. We create this small curve, and we can have the slope. Then we create the rest of this curve. So we calculate the slope from the measurement between 85% till 100%, and then we have this curve being available. So each manufacturer has its own R curve. The better accuracy of this method, because as we said, the hemoglobin has different four forms, which is the oxyhemoglobin, deoxyhemoglobin, metahemoglobin, or carboxyhemoglobin. As for the second two types are not measured in the using Beers-Lambert law in the first method. So this results in a little bit inaccuracy. To improve this, we use this method, which is the R curve. Later, we will talk more about what is the carboxyhemoglobin and the metahemoglobin and their impact in the reading of oxygen saturation in our blood, in RBC exactly. So how this R curve calibration is made? We calculate the red and infrared signal in analog, and we change them into a digital signal. We have this ratio. Also, we pass a band pass filters to remove much of the unwanted artifact above and below the signal bandwidths. When we have this ratio, second, a lookup table, which is will be specific for each manufacturer, will convert the ratio. This lookup table will summarize this curve. So this lookup table will relate the ratio of the red and infrared signal after being filtered using a band pass filter, will be converted into SpO2 using this lookup table. Finally, a matrix will be used, a decision matrix will be used to decide if this data is reportable or not. Usually, the values of the SpO2 as we said, the SpO2 is the percentage of oxygen in the RBC, okay, which is oxygenated hemoglobin. We have different range. For example, if this reading is between 95% to 100, this means is a normal. If it's between 91 to 94, we have what we call a mild hypoxemia. 86 to 90 is a moderate hypoxemia. Less than 85% is a severe hypoxemia. As we said before, we should avoid during the making the R curve and to have the lookup table, we should avoid reducing the SpO2 saturation in the blood below 85%, because we will have a severe hypoxemia, and this will result in irreversible damage to the patient, to the subjects. For this, we avoid the measuring of the blood samples below this level in the case of the making the R calibration curve or R curve. So usually depends on the situation. So we make the reading of the pulse, the SpO2 using the pulse oximeter, and depends on the staff in the hospital or any other clinical situation will take will intervene or take some intervention based on these readings. If it's a normal, so it's normal. We don't need any intervention from the staff. If a mild hypoxemia, example, we increase the oxygen, so we provide the more pure oxygen or a higher oxygen percent, higher than the 21% available in the medical atmosphere using a medical oxygen supply, and the similar for the other conditions. So in the first part in this session, we have talked about the principle of pulse oximeters, especially what I have talked about the first generation. The first generation have many sources of errors which lead to inaccuracy in the readings and a real big problem for the medical staff or clinical staff. And we will cover this part to talk about these sources and how some of them have been corrected using the second generation, and the other part have been corrected in the third generation. So as we see in this chart, this is a normal signal. As we said, in the pulse oximeter, to have a good design, we have to address two parts. The first part, which is the electronics, as we said in the block diagram, and another part which we should address is a signal processing, which is very important here in the design of the pulse oximeter. We should have a good background in the signal processing. As we see, we have this polysome, we have this curve, plasmographic curve, which represents the oxygen saturation in the blood. This is a normal signal, so a normal AC signal, AC and DC signal. In case we have a motion artifact, as we see, this signal will be distorted. Also, we have a noise artifact, for example, as a result of this due to the motion. This is due, for example, to the power line noise, to the noise from the power line, like 50 Hertz or 60 Hertz, it depends on the country. And finally, we have a change in the signal due to a low perfusion. So this represents a normal patient with a good perfusion, without a patient motion, without a noise artifact. So we should address these errors. We now will talk about more source of the errors in the first generation. First of all, we'll talk about the strengths of the arterial pulse and how this will impact this signal, how will change this signal, the body movement as we see before in the slide, the presence of the dyshemoglobins such as the carboxyhemoglobin and methemoglobin, and how this will change the reading, the color interference and its impact on the reading of the SpO2. We have also the physical factors, the venous pulsations, and saturation below 80%, which is, as we said before, it's called severe hypoxemia. The strength of the arterial pulse. Another factor that reduces the arterial pulsation will reduce the ability of the instrument to obtain and analyze the signal is the hypothermia, the hypotension, and vasopressor use. So in case if we have a low temperature, a low pressure, or we use drugs which lead to the dilation of the blood vessels, this will lead to the loss of the strength of the arterial pulse, and will we have a loss of signal strength. Body movement, for example, in case of shivering or Parkinson patient. So Parkinson disease, a patient with a Parkinson disease, we will have a body movement which also lead to a noise in the reading. Another problem, as we said before, is the presence of the deoxyhemoglobin, like carboxyhemoglobin, and we will cover this topic in the third generation. We have the problem of carboxyhemoglobin, that the CO bond, which is a carbon monoxide, it have an affinity of 250 times than the affinity of oxygen. That means have a bond strength stronger 250 times than the oxygen. So the removal of this bond between the CO and the hemoglobin need a special intervention, and this in case of happening of the carboxyhemoglobin, this will lead to the loss of the ability of carrying oxygen to the tissues, and will lead to a poor perfusion, and finally to unhealthy condition. Metahemoglobin, similar to the carboxyhemoglobin, will minimize the carrying capacity of oxygen by the blood to the tissues, and will have unhealthy condition. And we will talk more about this in the part 3, which is called Pulse Co-Oximeter. The use of the color interference, for example, we are not talking about the color skin, the skin color of the patient. We are talking about the use of finishes like the nail finishes and other types. Physical factors which also could affect the signal, or the signal for pulse oximeter, is the using of electrical surgical unit, the use of non-invasive blood pressure cuff, which will squeeze the blood vessels, the high intensity light in the surgical units. Venous pulsation, we have a condition what we call AV fistula, where we have make a shunt between the artery and the veins for dialysis patients. This will lead to have a pulsation in the venous side, and as a result we have a misreading and an error in the reading of the pulse oximeter. A saturation below 80%, as we said before, also will have a bigger problem, because this will impact the R to R, the red to the infrared ratio. This model we have talked before. This is a model of the absorption of the different tissues in the finger. As we see, we have the absorption made by the arteries, we have the absorption made by the venous, by the veins, which is the venous absorption, and we have the absorption made by the rest of tissues. The only AC signal available in this model is in the arterial side, which is have the nature, as we said before, it's aperiodic and have a specific shape, as we see here, whereas the rest of the signals are DC signals. Another point, as we said before, from signal processing point of view, we have an AC signal which is really small by comparison to the DC signal. However, this model does not take into account the patient movement. For this, this lead to an error in the first generation. So this is the real model in case we don't have a patient motion. Here we will now talk about the use of the two wavelengths with digital filtration in the second generation. So in the second generation, we'll now address the problems which we have talked before about the source of errors. We will talk mainly about the motion and how this problem will be solved. We will talk about the impact of the perfusion, of having a low perfusion, and how we fix it using the digital filtration. As we report, it's an important part in the design of the pulse oximeter is the signal processing, and this will be clarified in this part. So as we said before, we have many problems in the pulse oximeter, the motion and artifacts, as we see before. We have the perfusion, we have the dyshemoglobins, and finally the accuracy. In the second generation, will we address the motion and artifact and the perfusion, and the third part, or the what's known as a pulse co-oximeter, which is a real device very similar, which give results very similar to real lab co-oximeter, will be solve this problem, which is the availability of dyshemoglobins in the blood of the patient. So we'll start now the source of the error, which is the motion artifact. As we said, in case of the motion, we will have another AC signal which was not taking into account in the previous model, which is in case we don't have emotion. In case we have motion, we will have another AC signal, but now we'll have this AC signal in the venous side, not in the arterial side. But we can differentiate between the arterial signal and the venous signal, AC signal. The first notice for, or the first difference between these two signals, that the arterial signal, as we said before, is periodic and also have a specific form, okay, as you can see here. So it's periodic with specific shape, whereas the AC signal from the venous part, which is the result of the motion, first of all, we can see it's random, depends on the motion and the speed of the motion. It's non-periodic, or what we call aperiodic as a signal processing. It doesn't have a specific wave, which can help us to eliminate. So as we said, this problem can be solved using the signal processing. So and this was used in the second generation. This another point, which is will be covered in this lecture, is the case of we have not only a patient motion, which was not addressed in the first model, this is the second model, but also another problem in case we have a low perfusion. Low perfusion will lead, for example, as we can see here, the saturation in the arterial side, like 98% in a good perfusion, and 88% in the venous side. So before the capillary and after the capillary, we have the amplitude, the saturation 98%, where here it's 88%. This results in a total SpO2 signal in 93. In case we have a poor perfusion or a bad perfusion, what will have this gap between the arterial side and venous side, in addition to the motion problem, will be much bigger. For example, this will lead a high drop in the oxygen saturation in the venous side. So for example, here we have a 10% gap, where here we have like around 48% gap. This will lead to a misreading in the SpO2. So the two problems will now be covered. Both are solved using signal processing. This is important of studying signal processing in the biomedical engineering. This helps to solve these two problems, because this problem will result being unable to read the oxygen saturation in the patient. So in the first generation, as we said before, we first digitized, filtered, and normalized the red and infrared signal. Each one of them has AC and DC signal. Then we will have the R and infrared ratio. Then, as we said, we have the lookup table, which is based on the R calibration curve. Then we can finally calculate the saturation. But the problem, as we said, in the first generation, if we have a patient motion, we cannot have a read for the oxygen saturation. Also, in case of low perfusion or poor perfusion, we cannot have a read for oxygen saturation. So in the first generation, the commercial manufacturers for the pulse oximeter have used the three techniques to solve them. One of these techniques is to freeze the last good value. For example, in case we have a patient motion, this will lead to unavailable reading of the saturation. So they make freeze for the last good value. This technique have been used by one of the manufacturers, for example, GE in Nalcor. The another way to solve this problem, usually when we take the value for the SpO2 percentage and heart rate from the pulse oximeter, we take the average. The average can be, for example, for 3 seconds, for 6 seconds, or even for 12 seconds. Usually, such manufacturers, to solve this problem, they take for a longer period, which also is not a solution. Such technique have been used by manufacturers like Criticare. And also we have other manufacturer has solved this problem by putting a zero value. They don't have any value during in the case of low perfusion or in the case of the motion. So in the first generation, the manufacturer have used one of these three methods, either freezing the last good value or taking the average in a longer period. Or giving just put a zero value to address the ability being unable to read the SpO2 in case of, as we said, in case of low perfusion and motion. So how these problems, which is the low perfusion and the motion artifact, has been solved in the second generation. We can see this block diagram for the Nalcor company with this model. They used the conventional pulse oximeter reader. As we said, we have a measurement and they add what we call a confidence in this measurement. How much is the confidence in this measurement? And they used an adaptive filter. As we said, they used what known as signal processing. We have used signal processing. And for example, in the case of the motion, we can easily discriminate between the AC signal from the venous and the AC signal from the arterial, being this one is a periodic, this one is non-periodic, this have a specific wave shape or waveform, this have a random waveform. They used an adaptive filter to solve this problem, and they give a measurement of the pulse oximeter, a second measurement of the pulse oximeter with the confidence on it. So finally, we have what we call the confidence-based arbitrator. This helps to decide what is the better reading, the conventional one or the one calculated by the adaptive filter. And based, finally, we have this result. Another manufacturer, which is Philips, saves the same problem, but not like this one using two readings with the confidence and but rather directly through use a filter, a digital filter. All these filters are a digital signal filters. It's called FST, and they solve this problem. This filter is known by Philips as FAST. It's named by Masimo. This mainly was developed by Masimo and used by Philips. Similarly, the adaptive filter is made by Masimo, but it's used by Nalcor. So both digital filters are developed by the Masimo company. The Philips names this filter as FAST, which is an acronym of Failure Artifact Suppression Technology, where the best solution was available in Masimo. Their technology, they call it SET, which is a signal extraction technology, is an acronym for signal extraction technology. They have used many filters, one of them called DST. One is the FST, which have been used, as we said before, by Phillips, and they name fast. The SST also algorithm, and other algorithms, the adaptive filter, which has been also used by Nalcor. So as we see, we have different engines. We call these engines. Each engine has a measurement and a confidence. For example, I have confidence by in this case like 20%, in this one 50%, and so on. And finally, we have the confidence-based arbitrator, which decide based on the confidence which is the best result or the best value of the oxygen saturation. So, as we said before, the second generation has been developed to solve the problem of the poor perfusion or low perfusion and the problem of the motion. This has been solved using these digital filters, or what we call parallel engines. This is an explanation of one of the filters, which is the DST, the discrete saturation transform, and how it solves the problem of the AC signal, which is the motion, which we call have been called in another way as adaptive filter. So the DST filter has been used to solve the patient motion. For the perfusion, the problem has solved in another way, but also signal processing. We have talked in the part 1 about perfusion. I'm not going to talk another time for this about this topic. Here is the perfusion, and in case we have a bad perfusion, and what will impact. This is the SpO2 signal. As we can see, we cannot have a reading with in the case of we have motion, and this is the first generation. What will really happen, as we can see, we have the red signal and we have the infrared signal. As we see here, we have a great drop in the absorption of the red signal. We have the transmission, sorry, not as absorption, the transmission of the red signal will be lower, whereas the transmission of the infrared signal will not be impacted. Okay. To calculate the perfusion, or to calculate what we know as a perfusion index, we use the infrared signal from the reading. We have infrared signal and red signal. We focus only in the case of the perfusion. To calculate the perfusion, we use only the infrared signal. As we can see, we have a very low transmission of the infrared signal. As you can see here, it's similar to the above slide, to the previous slide. We see that we have, as we said before, each signal, red and infrared, have AC signal and DC signal. Here, in the case of perfusion, the infrared signal in a normal case, this is the DC, which is very large, and the AC signal is small. Whereas in the case of a bad perfusion, or low perfusion, or poor perfusion, what will happen? The AC signal will still the same, whereas the DC signal will be dropped, as we see here. So the ratio of AC to DC signal of the infrared signal will give us about, if in case we have a good perfusion and low perfusion, and this help us to determine what is the best reading of the SpO2. Usually this perfusion index ranges from a value 0.02% to a value 20%. 20% means that we have a really good perfusion and a healthy person. In case of 0.2 means very weak signal or very weak ratio, and this means we have a really bad perfusion, and this could lead to a serious damage to the patient, or a serious harm to the patient. So this, as we said, the perfusion is an early indicator of deterioration for the patient. So this is the addition of the second generation. First, it helped to give a more accurate reading of the SpO2. Second, it gives us a new parameter, which is the perfusion index. Also, we have another parameter, which we'll talk now about it. It's called the perfusion, the plus variability index, is a measure of the dynamic change in the perfusion index. This means the variation in the value of perfusion index in the same patient for a long time. Like example is similar to the measuring of the heart rate variation of the patient. This also very important, which can give us information about this patient, and in case of the deterioration of the health condition of this patient, and how we should intervene. So, as we said before, we have two problems: the motion artifact and the perfusion, and both of them have been solved in the second generation using the signal processing. The first problem is the motion has been solved through a filter known as DST. The second problem, which is perfusion, the motion has been solved using DST. And the second problem, which is perfusion, has been solved using the perfusion index, which is calculated using the infrared signal by putting the ratio of AC to DC, which should have a value between 0.02% up to 20%. And based on this value, this helps to enhance the accuracy of the reading of the pulse oximeter. So in the second generation, we have solved the problem of the motion and the problem of perfusion using filtrations and adaptive filters, as we said and discussed before. Now we'll move to the part 3, which is the third generation, which have solved an important problem we always faced in the case of reading of the pulse oximeter, which is the presence of the dishemoglobins, or what we call it non-functional hemoglobins, such as the carboxyhemoglobin and metahemoglobin.